Alright, so hi everyone, I'm Karthik, and before we start with our main project, what I want to do is we will go through all the basics of the particle simulation. Okay, so let's create a geometry network. I'll call it sample. I'll change the color here, something like this. Let's create a sphere inside this. This sphere, I'll change the primitive type to polygon, and I'll also change the frequency to 20. So we have a lot more points here. Okay, a lot more geometry to work with. I'll also move the center to 0, maybe 1 in the y direction. So we have moved the sphere up in the y direction by 1 value of 1. So this is our sphere and this is going to be our source. Okay, and we are going to generate particle simulation on the surface of the sphere. Okay, so this sphere is our source. Okay, and I'll connect this to our pop network. So this is our pop network. So pop network is basically the DOP network where all the particle simulations takes place. Okay, let's call it particle sim. And if I turn this on, as you can see, this sphere, which is our source, is connected to the first input of our DOP network. And if I turn this on, you can see on the very first frame itself, a lot of particles are being generated, as you can see, on the surface of the sphere. And if I run the simulation, if I play this, you can see a lot more particles generate as we move along our timeline and as the simulation takes process. Okay, so let's dive inside our DOP network, as there's a default setup here, and this is our default setup. So inside our our pop network, you will find a pop source. This pop source is where we generate our particles. Okay, this pop object is where we store our particles, and this pop solver is a brain of this particle sim. Okay, so in the pop source, we generate our particles and we define where we are going to generate our particles. By default, you can see that we are emitting our particle scatter on the surface. So that means we are emitting or generating our particles on the surface of the sphere. Okay, there are a lot more properties here that we can look into, but we will just keep it at default. The other thing is geometry source. So this is asking what is the source where we are going to generate our particle, or where the particle simulation needs to take place. What is the source? So the source geometry is our first context geometry. As you have seen here, the sphere is connected to the first context of our pop network, and that is what we have defined here. So use first context geometry, which means the first geometry that is connected to this input. We can also change it to second, and then we will have to connect the source to here, or maybe if I change it to third, then here, and so on and so forth. Another thing that we can do is we can also use a swap path here. Okay, so if I do not want to connect our source to our pop network, I'll create a null. I'll call it source. I'll copy this, and in this swap path, just paste it, and now we have our source. Okay, we have a guide here, and we can turn this off. So now you can see that particles are being generated on the points, I think, on the sphere, because we have by mistake changed the emission type. I'll just keep it to scatter on surface, and now you can see that the particles are being generated randomly on the surface of the sphere. If I play this, this is what we are getting. Okay, so this is our source, and we have a lot of properties here. The other thing on the source tab, we have source group and emission attribute. So what if we have a sphere? Okay, so this is basically our sphere, and we have created a group here, and that group only consists this area. So all these points which we have selected are in a specific group, and what we want is, when we run the simulation, we only want the particles to be generated on the selected part of the sphere. So we can do that with the help of a group. Okay, I'll just create a group, and this group is by default primitive. We will change it to point. Let's name the group anything like gen for generate, and by default the base group includes everything, but we do not want that. We will turn that off, and we'll come to keep in bounding region, turn this on, enable this, and now we will, with the help of this bounding box, we will decide what part of the sphere is in this group. So we have selected this part. Everything that is in this bounding box is in this group called gen. Okay, and what we can do now that we have a group, we can go to our particle sim, and in the source we can select our group. Source group is going to be gen. So now you can see that all the particles that are being generated are generated only on the surface of the sphere, which is part of group called gen. Okay, if I run this, you will see that the particles are only generated on the area which is in the group gen. Okay, the other thing that is notable here is emission attribute. So if I just remove this, we can also control the area or the part of the sphere which will be generating or which will participate in the particle simulation but with the help of an attribute. Okay, so if I just delete this group, we have our sphere, and what I'll do is I'll generate attribute adjust float. So this node is creating an attribute for us, which is p scale. I'll just change it to mask. So we are creating an attribute called mask. Change the operation to set always, and I'll change the pattern type to noise. Okay, so we have a attribute, and the value for that attribute is going from 0 to 1. Okay, now let's visualize this mask attribute. As we are visualizing this mask attribute, you can see that it is being represented by a color ramp. I'll just change it to grayscale here, and now you will be able to understand it better. Everything, so we have a mask attribute, and the value for that mask attribute is going from 0 to 1. Okay, and now you need to understand that we are representing this mask value 0 to 1 on our sphere with a color ramp that is going from black to white. So everything that has a white color has a value of 1, and everything that has a black color has a value of 0, and everything in between, like something like this gray, has a value somewhere here between 0.5 between 0 and 1. So if I make it a little bit contrasty, you will see this. Okay, we have white area and we have black area, and as I said, all the white area has a value of 1, mask value of 1, and all the black areas have a mask value of 0. Now if I use this mask attribute in our pop network, what will happen? Let's see. I'll go to our emission attribute, and what I will say is that let's select our mask, and what I'm saying to our this default network is that generate particles only on the areas which has a mask value of 1. Okay, This is our sphere. This is our mask attribute. This area has a mask value of 1, this area has a mask value of 0, and we are only generating on the white area, on the area which has a mask value of 1. So let's run this. If I run the simulation, you can see simulation is taking place, but only in the area which has a mask value of 1. Okay, so we've gotten here two very nice way of controlling where we are generating our particles. One is emission. I think I always prefer to do it with emission, and in the future tutorials also you'll learn this, that emission attribute is one of the better ways of doing or controlling where the particles are going to be generated. I'll just delete this. Okay, I'll turn off the attribute representation, and you can see if I run this simulation, it is running pretty nicely. Let's go to a bird tab, and this section is pretty important too, and it's actually very interesting. When we are running the simulation, you can see particles are being generated on the surface of the sphere. But how many particles are being generated, and how many particles are being generated per second, how many particles are being generated per frame, how long will this particle, how long will these particles live? These are the things that we control in this tab. Okay, so let's go to our frame 24, and instead of control 5000, I'll change it to 100 so that it's better for us to understand things. So on the first frame, you can see there are a couple of particles here. Okay, but if I run this simulation, a lot more particles are being generated. Okay, but how many particles are we generating on 1 second? So 1 second here is 24 frames. So if I come to 24 frame, how many particles are being generated here? 101 points. Okay, so here these values come into play. How many particles, now listen this very carefully, how many particles we need to generate per second, we will control with the help of constant birth. This constant birth rate controls how many particles are being generated per second. Okay, so on frame 24 we have 101 points, and this is approximation. Okay, on frame 48, if in 1 second we are generating 100 particles approximately, then in 48 frames or 2 seconds we will be generating 200 if the math is correct, right? And you can see approximately 203 points. We are controlling how many particles are generating in the simulation per second with the help of this constant birth rate. If I increase it to 10,000, and if I run the simulation again, this is what we are getting, and in 1 second, that is 24 frame, we should be getting approximate 10,000 points. So yeah, we are getting 10,005 points. On 48 frame or 2 second, we will be generating 20,000. So yeah, we are getting 20,005. Similarly, in 3 seconds, we'll be getting around 30,000 points, and so on and so forth. Okay, so if you want to control how many particles are being generated per second, then you will play with this value. Okay, you will write your intent here. Okay, this is where you put the value. But what if you want to control, you want absolute control, you want to control how many particles are being generated per frame, and you will decide that here, impulse activation. Just turn this off and we'll come to an impulse count. So if I write 100 and I play this simulation, you can see that I have said this impulse count should be 100. That means every frame generate 100 points. So if I am generating 100 particles per frame, then in 24 frames I should be generating 240 points. And sorry, 2400 points. Yeah. 24 into 100 is 2400. So we are generating 2400 points in 24 frames. In one frame, on the first frame, we are generating 100 points as we have decided here. In second frame, we should be generating 200 points. In third frame, we should be generating 300 points. And if I come to 48 frame, then 48 multiplied by 100 should be 4800. And we are getting 4800 points. If you want absolute control and you want to control how many points are being generated per frame, then you will play with the impulse count value. This impulse activation and impulse count is for per frame basis. Okay, how many points or particles need to be generated per frame, you decide here. Constant activation and constant birth rate is for per second. Okay, now you have decided that you know how many particles you want to generate in your simulation. Okay, you are running a simulation for 150 frames. Okay, and in this complete simulation you want around 100,000 points. So I'll come to the constant birth rate. Okay, and when we run the simulation, you will see that in 1 second we are generating 100,000 points. In 2 frames you would be generating, I think, 200,000. Yeah. In 3 seconds you would be generating 300,000, and so on and so forth. Okay, if you want absolute control how many particles are need to be generated in one frame, then you will play with this impulse count value. And if you want to control how many particles needs to be generated per second, then you will play with the constant birth rate. Okay, very important. Impulse count is per second, and constant birth rate is, impulse count is per frame, and constant birth rate is per second. I'll say it one more time. If you want to control how many particles are being generated in 1 second, then you will play with this constant birth rate value. I do most of my simulation here only. Okay, if you want absolute control how many particles needs to be generated in one frame, then you play with the impulse count value. Okay, so this is the basic of how can we control how many particles needs to be generated in your simulation, in what time frame also. Okay, this is maximum points per frame, so this is the upper limit, and I think the upper limit is 1 million here, that can be generated per frame. So if you come to the impulse count and you write 10 million, then it will not work. You will have to change the setting here. Okay, change the setting here. Okay, just born grow up. We will learn this in some other lesson. It's not important in this one. The next important thing is life expectancy and life variance. Okay, so now I am generating, let me just keep it to 1000. Now we have decided that we need to generate 1000 particles per second. Okay, but what is the life? How long these particles are gonna live? We decide that here. Each particle that is being generated in the simulation will live 100 seconds, as we have decided here. Life expectancy, how long the particle will live in seconds. If I change it to 1, you will see that the particles will start disappearing after 1 second, after they have lived 1 second. Okay, so if I see this, you will see that constantly the particles are birthing and then they are dying. If I increase it to 10, you will see that the particle will stay for at least 10 seconds, which is more than the scope of our time frame here, our timeline here. So they are going to live for almost the current whole timeline. If I change it to 2, you will see that particles will live for 2 seconds and then they will die. So we are deciding how long the particles will live here, life expectancy. Okay, if I set it to 5 seconds, the particles will live for 5 seconds and then they will die after that. Okay, let's just keep it at 2 and run the simulation again, and you will see that some of the particles are birthing, some of them are dying. They birth, and when they have completed their life expectancy, which is 2 seconds, when they have lived long 2 seconds, they will die. Okay, but we do not want all the particles to have the same age. Okay, what if you decide that you have 1,000 particle, you are generating 1,000 particle per second, and all those 1,000 particles needs to have a different life variance. You do not want them, all of them, to die at the same time. You want some particles to die at 2 seconds, you want some of them to die at 1.5 second, you want some of them to die at 2.5, and we do that with the help of life variance. Okay, so the basic life expectancy that we have set is 2 seconds. What if I increase the life variance to 1? So what life variance here does is it creates a range, okay, for the life expectancy of these particles. And what will that range be? It will plus and minus from the life expectancy, that is 2. I'll just explain it here. Life expectancy is 2. Life variance, if we have set it to 1, then all the particles will have a life which will range from 1 to 3, because life expectancy we have set as 2. We want all the particles to live at least 2 seconds, and then we have given a variance of +1 and -1. Okay, so the range will be 1, 2, 3. The particles randomly, they will live for at least 1 second, and the highest range will be 3. So the age will be between 1 and 3 for all the particles. Okay, so now that we have covered the basics of our particle simulation, we will go through the main project. So let's create a geometry network again. I'll call it sim, change the color to something like this. Okay, and what we can do is we will create first the source which will be emitting our particles. Okay, so in this project, what I want for the source to be is, I want it to be a boundary like structure, something like this, and I want it to emit particles, and those particles I want to get attracted towards center to a mesh. Okay, so let's create a box, and this box let's increase the size to something like 2.13, the uniform scale, and decrease the size in the y direction to maybe 0.11. Let's move it up a bit in the y direction, something like this. Okay, and in my main project I have increased the axis division here to something like, I think it was 14 by 13 by 37. So we have inner geometry here. Okay, to create our boundary, what I want is all the primitives which are facing in the positive y direction and all the primitives which are facing the negative y direction, I want to delete them. So let's first create a group which will select them. I'll create a group node. I'll call it delete. the group type is going to be primitive, but I'll just turn off the base group here. Okay, the base group selects everything, so we do not want that. We want to turn on the keep by normals, so enable it. Okay, and we want to select all the parameters which are facing the positive y direction. So we'll go to our direction, change it to positive y, and we will decrease the spread angle. Okay, so we have selected all the faces or parameters which are facing the positive y. Now what I want is I want to create another group, and this group will select all the faces which are facing the negative y direction. Okay, so change the direction to -y, and voila, we have our faces in the -y as well. But come to the group 2, and here we will, the initial merge, we will change it to union with existing, because we have kept the name of the group to delete in both the group nodes, and this will just merge both the selections. Okay, and now we can create a blast node, and we will delete that. Okay, now we have a boundary. Another thing that I'm gonna do is I want to give some depth to this, so I'll create a poly extrude node and move it by a distance of 0.005. Okay, so we have some depth here, and turn on the output back, so we have faces, so we have faces in the back direction as well. Okay, now let's create our attribute adjust float node, and here we will create our mask attribute, and with the help of the mask attribute we will decide which areas will emit the particles and which will not. So I have already turned on the mask attribute visualization, so that this is that. Okay, we'll change the operation to set always, change the pattern type to noise, and the value is going from 0 to 1. Okay, and you can see that those values 0 and 1 are being represented by a black and white color. Okay, so all the areas which have a black color have a value of 0, and all the areas which have a white color have value of 1, and the rest of the area which has a gray color or color between black and white has a value between 0 and 1. Okay, I'll come to the element size, and I'll decrease the element size to 0.132, something like this, and we are getting some better fluctuation in our mask values here. One thing that I can do is I'll create a subdivide node and change the subdivision depth to 3, and now when I visualize the mask attribute, you can see there's enough geometry or enough resolution for us to properly see it. Okay, so with the help of the mask attribute, we have given this geometry value between 0 and 1, the mask attribute value between 0 and 1, and we will be using this mask attribute to emit particles from our source. I'll just make it a bit sharper, something like this. Okay, so this is our source. I'll create a null called pop source. Okay, and we can create a pop network and have a look. So I have connected our pop source to our pop network, and if I run this simulation, you can see that particles are being generated on the surface of this source. But as we have already decided, we want the particles to be emitted only on the areas which has a mask value of 1. So we'll come to a pop network. Here in the pop source, we will turn off the grid, and we can see the particles. The emission type is scatter onto surface, which is correct, and we want to scatter the particles or emit the particles from the surface of this boundary. Geometry source is the first input context, which is correct. Source group we have not created, and the emission attribute is going to be mask. So if I come back to frame 1 and run the simulation, you will see that all the surface area which has a mask attribute value of 1 is emitting particle. Okay. I'll come to our source and go to birth tab and increase the constant birth rate to 50,000. Constant birth rate, as I have told you in our basics, this decides how many particles are being generated in 1 second. So 50,000 particles will be generated in 1 second. And this is just for references of these values. These are not final values. I'll just decrease the life expectancy to 1, life variance to 1. So the life attribute of all these particles is going to vary from 1 to 3. Okay. 2 minus 1 is 1 and 2 plus 1 is 3. So 1 to 3. Let's run this and you can see that particles are being generated. They are also getting deleted as their life attribute reaches the end, and new particles are being generated. Okay. So we want all these particles to go towards the center or get attracted towards the center or towards an object. So for that we are going to use a pop node called pop attract. This is a pop force node. Okay. And this basically attracts the simulated or generated or emitted particles towards a certain point or certain position or certain surface points. Okay. If I run this now, all the particles are getting attracted to the center. Okay. I can move this here and you will see that the particles will get attracted to this. If I move it outside, you will see that the particles are getting attracted to this position. Right? So I'll just keep it here at the center. And this is what our pop attract node does. Okay. But we don't want to attract all these particles to a single position or single point. We want to attract it to a mesh. Okay. And we also want a collider here. So let's go outside. And now what I'm going to do is I'll create a font. I'll change the text here to K. K is my initial, that's why I'm using it. I'll change it to 90, maybe something like minus 90. So we have K. And if I look at it from top perspective, this is what I'm getting. Okay, which is actually nice. Let's create a poly extrude for this also. And let's increase the distance to 2.12. Sorry, 0.212. Something like this. We'll turn on the output back. So we have a complete mesh. And also increase the divisions to 6. Okay. Detailed geometry for our collision. So what we can do is create a null. I'll call it collide. So this is going to be our collision geometry. Okay. I also want all these simulated particles to get attracted to this K. Okay. And we can do that better if we create a scatter node and scatter. Sorry, not scatter and align, but scatter node. And we will scatter around 1,000 points here. Okay. On the surface of this mesh. So all the particles that we will be generating from the boundary source, they will be coming towards all these points. They will get attracted towards these points. Okay. And that's what we want. So let's create a null and call it pop attract. Alright, we can go to our pop network, go to pop attract and change the attraction type. Instead of position, we will change it to surface points, and the swap path we can just copy our pop attract null and paste it on the swap path. Okay, so now if I run the simulation, you will see the particles are actually getting attracted to the surface points, but we do not have any, but because the force is one, they keep moving outside also, and there's nothing for collision also here, and for that is why they are behaving like this. Okay, so we will improve this by creating a collider here. So I'll just create a merge node. Okay, and I'll create a static node and I'll connect it to merge and come to affector relationship and just change it to mutual. Okay, so what this means is that the collider and the simulated particles are affecting each other. Okay, this is what I usually keep this to, and it works perfectly well for me. I'll come to the static object and we need to point it towards our collider. So I'll just copy this collide null, go to our static object, come to the swap path and paste it. Okay, and now you can see that we have a collider here. I do not want any bounce here on the collider. So when the particles collide with this, I do not want them to bounce around. Okay, I'll come to the physical, and everything seems fine for now. Let's run this simulation.